So the first speaker is the Ryan Endsley, who is talking about a wide area view on reionization with MMT and ALMA, exploring massive redshift 7 galaxies and their host ionized bubbles. Go ahead, Ryan.
Okay, yeah, so for those of you who don't know me, my name is Ryan Endsley. I'm a student at the University of Arizona. I work primarily with Dan Stark, though the research that I'll talk to you about today has involved a number of other collaborators listed here at the bottom of the slide. So what I want to talk to you about today is a 3-year campaign we've been conducting with MMT Binospec targeting Lyman-alpha emission from UV bright massive Lyman bright galaxies identified across a very wide area of fields. Specifically, this survey has been focused on the XMM and Cosmos fields, which total about 7 square degrees of imaging. So what I'll describe in this talk today is how, with this survey, we have been able to, 1, identify likely large ionized bubbles at redshift 7 via clustered Lyman-alpha emitters in our sample, 2, quantify the galaxy overdensities in these likely reionized regions, and 3, uncover details of Lyman-alpha transmission through the IGM at redshift 7 in these massive galaxies that's necessary to place our results in context of reionization. So first off, I just want to give some quick details about our survey. So far, we've observed over 90 massive redshift 7 Lyman bright galaxies. We have over 30 Lyman-alpha detections at redshift 6.5 to 7.1, and a subset of our massive redshift 7 galaxies have also been observed with ALMA via the Rebel survey. So the first results from our Lyman-alpha campaign have been described in 2 papers already published earlier this year. I'll quickly go through those results and then move on to what's new. So here on the left, I just want to quickly show the subset of Lyman-alpha detections that we had from these initial results that were published earlier. So from these initial results, one of the things we found is that the Lyman-alpha equivalent width distribution of our massive redshift 7 Lyman bright sample was similar to that we had from our redshift 6 Lyman bright sample that we targeted simultaneously. Okay, and what this means is that the Lyman-alpha emission from massive redshift 7 galaxies is not being strongly attenuated by the highly neutral IGM. And this is in contrast to the Lyman-alpha evolution seen in fainter systems, which does show a rapid decline consistent with what you would expect in this neutral IGM. Okay? So the question becomes, what's going on here? Why do we see this evolution in fainter systems and not so much in the massive galaxies? Well, one possible explanation is that this is giving us some insight into the structure of reionization. Perhaps what we're seeing here is the effect of massive galaxies commonly sitting in large ionized bubbles powered by strong overdensities. Okay, these bubbles allow Lyman-alpha photons to cosmologically redshift before encountering the neutral hydrogen, increasing their transmission through the IGM. Another effect that we might be seeing here at the same time is that massive redshift 7 galaxies have large Lyman-alpha velocity offsets, which effectively give the same effect of boosting the Lyman-alpha transmission through the IGM by pushing the photons into the damping ring. So what we want to do moving forward is we want to better understand, kind of the contribution of both of these effects. So we're tackling this in 2 ways. One, we're building up a data set to identify and characterize likely large ionized regions at redshift 7 across these wide area fields that we're targeting. And at the same time, we're obtaining deep Lyman-alpha spectra of our massive galaxies to explore how their Lyman-alpha line profiles impact the transmission through the IGM. So with the ionized bubble picture, we're tackling this primarily in the Cosmos field just due to the deeper imaging available, allowing us to push fainter down the luminosity function. So our goal here is to identify the regions of clustered massive redshift 7 galaxies showing Lyman-alpha emission across the Cosmos field to determine whether these regions coincide with galaxy overdensities, and moreover, to characterize the extent of the Lyman-alpha emitters within these regions, giving us some insights into the extent of the possible ionized bubble that they sit inside. So from our first results, we noted that we had 3 extremely nearby massive redshift 6.8 galaxies showing Lyman-alpha emission in the Cosmos field. So all three of these galaxies are separated by less than 5 arc minutes, and they reside within a redshift interval of 0.06. All of these galaxies are contained within a radius of 1.7 physical megaparsec sphere. And just based on these massive galaxies, the number counts compared to what we have from the luminosity function suggest that these galaxies are tracing a overdensity of about 4 times the number of galaxies on 5 arc minute scales, 2 physical megaparsecs, if you want to think about it that way. So the question then becomes, are we seeing perhaps one of these instances where these 3 galaxies are kind of residing within this more extended, larger density that's powering this very large ionized bubble? Well, to kind of gain more insight into whether this picture holds, we need to better characterize the overdensity across a wider area. And we can do that, obviously thanks to the fact that these cosmos fields probe such a large area. So we've identified a total of 12 massive Lyman break galaxies with photometric redshifts consistent with redshift 6.8 in the surrounding 11 by 15 arc minutes squared, right? And we actually have another Lyman-alpha detection in the same region at a higher redshift 6.88, possibly suggesting that what we are seeing here is really this more extended overdensity, but we need to test this. So we conducted ultra deep, about 20-hour Lyman-alpha follow-up of the majority of these remaining candidates with the goal of quantifying the overdensity in this extended region and better determining the possible extent of the ionized bubble. So what did we find? We actually ended up with Lyman-alpha detections in 9 of 10 targeted galaxies across this region. All right, so that's a 90% Lyman-alpha confirmation rate in this region here, where all the Lyman-alpha detections have redshifts between 6.7 to 6.88. All targeted galaxies are massive, with UV luminosity spanning 1 to 4 times the characteristic UV luminosity, and all sources are contained within a sphere of radius 4.4 physical megaparsecs. Right? And now that we have this more extended region and 3D position information for these galaxies, we can determine that, based on these 9 massive galaxies, this region appears to be 2 times the average density across this very large scale, this 5 physical megaparsec, 15 arc minute scale. So, this is one bubble that we've been able to identify so far. We're still pushing on it. But, to better determine what these Lyman-alpha results are telling us about the structure of reionization, we also need to understand how the Lyman-alpha line profiles are assisting in boosting the Lyman-alpha transmission of these massive galaxies. So we're able to do that thanks to the decent resolution spectral resolution that we get from our Binospec spectra. And we're also combining our results for a subset of sources that have C2 measurements from the ALMA Rebel survey. So I'll quickly go through those results in the remaining minutes. So what do we find from our Binospec spectra? Well, we're finding broad Lyman-alpha line profiles in our massive redshift 7 galaxies, as you can see here. Substantial fraction of the photons are being pushed to high velocities purely as a result of their line profiles, which is boosting the Lyman-alpha transmission through the IGM. So for reference, fainter galaxies show full with half max values of about 200 kilometers per second. We're also finding multi-peak line profiles in a subset of our massive redshift 7 galaxies. And with our C2 measurements, we're able to place our line profiles into the systemic frame. So what do we find? Well, we find that all of the peaks that we're seeing are redward of systemic. Now, I don't have time to dive into the details, but if you're interested, please ask me after the talk. We're also able to measure the Lyman-alpha velocity offsets of our sample, and we're finding velocity offsets that are systematically large, greater than 100 kilometers per second. And this suggests that these velocity offsets are indeed likely boosting Lyman-alpha transmission through the IGM among these sources. With our sample, we've been able to double the number of velocity offset measurements among extremely luminous MeV less than minus 22 galaxies at redshift greater than 6. And combining our results with that literature sample, we find an average of 325 kilometers per second among these extremely luminous galaxies, consistent with model predictions. So in summary, we have this ongoing redshift 7 Lyman-alpha program targeting redshift 7 galaxies across very wide area fields, we found that the Lyman-alpha equivalent width distribution does not strongly evolve between redshift 6 to 7 or the massive Lyman break galaxies. We're beginning to identify and characterize likely large ionized bubbles at redshift 7 across the cosmos field. And we've indeed found one instance where we detect Lyman-alpha in 9 of 10 massive targeted galaxies at redshift 6.7 to 6.88. That spans a large-scale overdensity, 2 times the number of massive galaxies than I expected on average, across a 5 physical megaparsec scale region. And this could potentially be powering a very large ionized bubble within this volume. We're at the same time with our survey, we're beginning to improve our understanding of Lyman-alpha line profiles on IGM transmission. We find broad Lyman-alpha line profiles among our massive galaxies, and we also find large Lyman-alpha velocity offsets, meaning that a larger fraction of those Lyman-alpha photons are being pushed into the damping wing, increasing their transmission through the IGM. Take any questions. Thank you.
All right, thanks, Ryan. So time for questions. Yeah.
Yeah, it looks like we already have a number of questions. So it says, what are the Lyman-alpha luminosities? Also, do we know that they are really are massive galaxies, and what are their masses?
Yeah, so about the Lyman-alpha luminosities, I haven't calculated those explicitly. That is something I can do. So sorry, I can't tell you offhand. I know that the equivalents range from about 5 angstroms to 40 angstroms in this sample. And they're all 25th, 26th magnitude, if that helps. The second question, sorry, what was the second part of the question?
Oh, do we know that they really are massive, and what are their masses?
So yeah, these galaxies, majority of them have IRAC photometry that is not strongly confused by neighboring sources, and I find masses ranging from about log m 8.5 to 10 to the 10. So, on average, about 10 to the 9 solar mass galaxies. Obviously, there are some galaxies in there that are closer to 8.5 that are just more bright because of the fact that they have more rapid star formation ongoing.
All right, thanks. So the next question from Rensky Smith. So the number of Lyman-alpha detections in your redshift 6.8 bubble is impressive, and the Lyman-alpha fraction seems even higher than that seen in sources at redshift 5. Do you understand why the intrinsic Lyman-alpha fraction is so high?
Yeah, so it is worth noting that the O3 plus H beta equivalent distribution in this region, I looked into this a little bit. It appears higher than that on average among the general redshift 7 population. So maybe what's happening here is that these galaxies that we're sampling are preferentially have a larger production of Lyman-alpha photons just by chance, or maybe there's some environmental effect. Something that I need to explore more. But I completely agree that's an interesting question.
Okay, so
yeah. So another question is: have you tried fitting IGM models of the neutral fraction to the combined sample?
I have not yet. No, that's something that I hopefully will be able to tackle next year. But as I said, the survey is still ongoing, so it's one of those things where we're waiting until we have enough data where we feel like we can really tackle that.
All right. So then the next question is Caitlin Casey, who is asking that what Galaxy overdensity does the redshift 6.8 structure correspond to?
So the Galaxy overdensity of this this region that I've described here. So it has 2 times the number of these UV bright massive galaxies than that expected on average across this region that's about 5 physical megaparsecs in scale.
Okay, you have a number of other questions. If you can answer them in Slack at your convenience, we should probably move on in the interest of time.